In this lesson, we will learn about lines that intersect circles. In particular, we will answer the following question. What is the relationship between a tangent line to a circle and the radius drawn from the center to the point of tangency? Now, a few vocabulary words that we require before answering that question are the following. We need to know what a tangent line is and what a point of tangency is. So a tangent line is a line that's in the same plane as a circle that intersects the circle in only one point. The point where a tangent and a circle intersect is called the point of tangency. So for example, this line M would be the tangent line. Remember, a tangent line is a line that intersects a circle only in one point, and the point where the line intersects a circle is called the point of tangency. So that would be point P in this case. We're going to conduct experiment in class from which we can conclude that if a line is tangent to a circle, then it's perpendicular to the radius that's drawn to the point of tangency. Now notice for a circle, there's a lot of radii. But if you take the one radius that's drawn from the center of the circle to the point of tangency, then this theorem says that this angle formed by points C, P, and another point on the line is going to be a 90-degree angle. Okay. In other words, line M is tangent to circle C at point P, so the line segment CP is perpendicular to the line M. Alright, so the following is a proof of this theorem. So suppose that line M is tangent to a circle C at the point of tangency, point P. What we're going to set out to prove is that the line segment CP is perpendicular to the line M. What we're going to do here is a proof by contradiction, or what's called an indirect proof. We're going to assume that CP is not perpendicular to line M, and then show that this leads to some nonsense. Since this would lead to a contradiction, we know that our initial assumption that CP is not perpendicular to line M would be false. So that we can find a contradiction, let's assume that CP is not perpendicular to line M. Then it has to be possible to draw some line segment CX so that CX is perpendicular to line M. The reason that's possible is because we're assuming that CP is not perpendicular to line M, so there must be some line segment that we can draw in, calling it CX, such that CX and line M do form a right angle. Okay. So suppose we have such a line segment that forms this right angle with line M. Then CXP is going to be a right triangle. But in a right triangle, the hypotenuse is the longest length. Notice here that CP would be the hypotenuse of the right triangle CXP. So that means that CP, the hypotenuse, has to be longer than the leg of the right triangle. Since line M is a tangent line, that's what we're assuming. We're assuming line M is tangent to the circle. It can only intersect the circle C at one and only one point, the point of tangency P, and all other points of the line M have to be in the exterior of the circle. This means that point X has to be in the exterior of the circle. But this allows us to conclude that CP is less than CX, since CP is a radius of the circle. This contradicts the fact that CP is actually greater than CX from it being the hypotenuse, the longest side in the right triangle. Therefore, the initial assumption must be false, and CP has to be perpendicular to line M. So in this lesson, we address the essential question, what is the relationship between a tangent line to a circle and the radius drawn from the center to that point of tangency? Now, if a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. This is called the tangent radius theorem.